So today, we're going to look at some really amazing new research about an AI that's basically a detective. Its job? To hunt for tiny, almost invisible, and incredibly dangerous cracks in things like bridges and airplanes. And as you'll see, it does it unbelievably fast. But let's start with a really basic question that, it turns out, is super complex. How in the world do you find a crack you can't even see? We're talking about a flaw that could be microscopic, but if you miss it, well, the consequences can be huge. Yeah, because we're not talking about a crack in the sidewalk here. We're talking about the bridges you drive over every day, the planes we all fly in, the power plants that keep our lights on. For these things, finding that hidden damage isn't just some engineering puzzle, it is quite literally a matter of life and death. And that brings us to this whole field of study called structural health monitoring. It's a field dedicated to exactly this problem, finding those hidden flaws before they turn into disasters. You can think of SHM as basically giving our infrastructure a regular doctor's checkup. Engineers use all sorts of sensors to kind of listen to a building or a bridge, collecting data on things like vibration and stress to spot the very first signs of trouble. And don't just take my word for it. The authors of the very paper we're digging into today put it perfectly. They say this isn't just important work, it's absolutely crucial for modern society. And that's really the mission that's driving all this research. So how have people been doing this up until now? Well, for a long time, engineers have relied on a method that's really powerful, but it's also really, really slow. Let's break that down. Okay, it's got this kind of technical name. GA-XFEM. I know, it sounds complicated, but it's really just two key parts working together. You've got a genetic algorithm, which does all the smart searching, and then you have something called XFM, which builds a super detailed physics model to check if the guesses are any good. Now, this genetic algorithm part is pretty cool. It works a lot like natural evolution. As you see here, it starts with a whole bunch of random guesses. Then it tests how fit each guess is, gets rid of the bad ones, and then creates new, hopefully better, offspring from the survivors. It's a brilliant way to search, but there's a catch. And here's the big problem, the bottleneck. That second step, where it has to check every single guess, that requires building one of those really complex, really expensive physics models using XFM. So yeah, the process is thorough, but it makes the whole thing just painfully slow. And this is where our AI detective finally enters the scene. Researchers came up with a totally new approach, designed from the ground up to just smash right through that bottleneck. So they kept the smart genetic algorithm part, but, and this is the genius move, they swapped out that slow physics model for a couple of really powerful AI tools. First, a holomorphic neural network, or HNN. Think of it like a super fast AI brain that's already been trained on all the physics, so it can make predictions almost instantly. Then they added something called transfer learning, which is like giving the AI a memory boost, so it gets smarter as it goes.
So let's put it side by side. The key difference is just night and day. See, the old way was stuck with that slow, clunky physics model for every single guess. The new way just subs in a lightning-fast AI brain and even makes the search strategy itself smarter. It's a total game changer.
And what that means is the whole process is just fundamentally better. That evaluation step is now completely supercharged. Plus, by splitting the search into a big, wide, long-range hunt and then a super-focused, short-range one, the AI can use what it's learned to zero in on the answer way, way faster. All right, this is cool. Let's actually watch this new process in action. We start here at generation 0. You can see it's just a big, scattered field of random guesses all over the place.
But look at this. By only generation 5, the algorithm has already thrown out a ton of the worst guesses. The population of possibilities is shrinking fast as only the fittest guesses survive.
Jump ahead to generation 20, and wow, you can see a really clear pattern here. The search is narrowing down big time, and the best guesses are starting to form these little clusters around the most likely spots. And then, bam! By generation 55, those clusters have all merged into one single, super precise answer. The AI detective has found its target. So, okay, we know the new method is a lot smarter, but the million-dollar question is it actually faster? Well, this is where it gets really, really exciting. Just take a look at this chart. The classic method, the old way, it took around 12,000 seconds. That's more than 3 hours of computer time. The new AI method, just 527 seconds. That's, what, under 9 minutes? I mean, the difference is just staggering. It's not even a fair fight. And it wasn't a fluke. Across all the different tests the researchers ran, it was the same story every time. The new AI detective was somewhere between 7 and 23 times faster than the classic method. This isn't just a small improvement, it's a massive leap forward. So a faster algorithm is great news for researchers, for sure. But what does this actually mean for the rest of us? Why does making this process faster really matter in the real world? Well, for starters, it means we can run safety checks on our aging infrastructure way more quickly. It means we can schedule maintenance more efficiently, saving time and money. But the most exciting part? This opens the door to the possibility of real-time monitoring systems that could warn us of a problem the moment it starts. And as the authors themselves conclude, their work isn't just about this one solution. They say it offers a promising avenue for a whole new generation of safety tools, all built by combining the raw power of AI with the solid principles of physics. And that kind of leaves us with one last really fascinating question to think about. If we can build an AI that's this good at finding one kind of invisible threat, what other hidden problems, maybe in medicine or in material science or things we haven't even thought of yet, will this kind of technology help us finally see and solve next?